So in section 4.3, we're actually going over things that you already knew, but we're going to try and sort of draw them together and make some connections with them. So the first thing to look at is that the section starts on page 205. And they have this really great drawing, and you should study this graph because it tells us a lot about the first derivative and how it's related to the graph. Then the other thing that they do is in this theorem 4, they go over the first derivative test, which we already talked about. So they give examples of why at a local max f prime is greater than 0, and then changes to less than 0. Why at a local max, even if a non-differentiable point, f prime changes from positive to negative. And then they give several other really useful examples that you really should study because they're quite useful. And in particular, what they say at endpoints, so that you can really get a handle on what happens if there's a local max or local min at the endpoint. Right? Then they start talking about concavity, and they tell you what you already knew about concavity is the function is concave up if and only if y prime is increasing, and concave down if y prime is decreasing. But they sort of go further and they explain what concavity really is. So we've been talking about concavity in sort of loose terms. So, my favorite thing that I always say is concave up holds water like a cup, concave down like you're wearing a frown. All right, that's concave up. That's concave down. And sometimes the concavity is not as obvious as all that. So for example, this is concave up and then this is concave down, right? We're concave up, we're concave down here. And then we're changing to concave up right here, just because this is sort of curving down and this is sort of curving up. Right? So there's a point of inflection here, even though there's not a horizontal tangent in the graph. So sometimes we see a point of inflection, which is a change in concavity, looking like a horizontal tangent, but it doesn't have to, right? So you can have a 45-degree tangent, right? So these are all points of inflection. So that's a point of inflection. And so if you weren't clear on point of inflection, it is a point where the graph changes concavity. And it can change either direction, from concave up to concave down or concave down to concave up, either way. All right, so what they're doing in their nice picture in the lower left of page 207, right, that's page 207 there, is that they're explaining that this idea of concavity that we've been having very loose, like curving down, curving up, like what does that mean? That actually has a very specific meaning, which I will show you as soon as I change my calculator setup, which was set up for something different. No, I don't want to delete that. Okay, we just want to unselect it. Oh, it's too late, I deleted it. Okay, fine. Anyway, here's our old friend x cubed, and I decided to use x cubed because it's a great example of concavity, concave down, concave up. So it's sort of your standard point of inflection. And I wanted to use the Casio because it has this neat feature that we can go shift sketch, and one of the things we can sketch is the tangent, and then it allows me to very niftily use the cursor to move the tangent point around. So that's really quite useful. I'm actually going to zoom in on it quite a bit here. There we go. This is my crude zoom. All right. So then you can see, for example, when I get to x equals -1, I have a fairly steep slope for my tangent. In fact, it's easy to figure out that the slope of that tangent is 3. That's easy to figure out analytically. And then you could also see, it's going up 1 and over 1/3, up 1, now we're over another third. If I go up again, I'm going to be at the point 0, 2, right? So it would go up 3 and over 1. All right, now here's what I want to show you though. As I move to the right with the graph, what is happening to the slope of the tangent? The slope of the tangent is decreasing. If you think of the slope of the tangent being a number, like here we're pretty close to slope of the tangent equals 1, right? Back here it was 3. As we come closer to the 0, to x equals 0, the slope of the tangent is now closer to 1. Now we start to see a slope of the tangent less than 1. Slope of the tangent is like 1/3 right there. So the slope of the tangent is decreasing as x increases. Now that is the definition of downward concavity, that the slope of the graph is decreasing as x increases. Now when we hit the point of inflection, we get the slope 0. And then as we proceed from there, so now after x equals 0, all right, we start to get the slope. As I go to the right, now the slope is increasing. So x is increasing and the slope is increasing. That's what we mean by concave up. So now the slope is up to like 3, right? Right there, the slope's going to be 3. Back here, the slope was 1. So as the x increases, the slope of the tangent increases. So here's the real definition of concavity, and this is what they're showing you on page 207. As the x increases, the slope of the tangent decreases. That's concave down. As the x increases, the slope of the tangent increases. That's concave up. All right, so then it is specifically for that reason that y is concave up if and only if y prime is increasing. So we can now understand that that's not a theorem, that's the definition of concave up. That's what we mean by concave up, is that the y prime is increasing. Now, it follows that since y prime is a function, y prime can only be increasing if its derivative is positive. Therefore, y prime is increasing if and only if y double prime is positive. Then likewise, y is concave down if and only if, by definition, y prime is decreasing, which happens if and only if, then by properties of derivatives, y double prime is negative. So that's how we know that y concave up if and only if y double prime is positive, y is concave down if and only if y double prime is negative. So again, something you already knew, a new context for it, and next we will talk about something else.